Hello grade 9 students. Welcome to this virtual class. I am Madhu Vadke. So far we have finished 3 chapters. In today's video lesson we will revise the first chapter, that is number system. We will recall and go through all the concepts that we have studied. We started with number line. Every point on the number line represents a real number. Real numbers are of two types, rational and irrational. And in this chapter, we revisited all the numbers that you have studied right from the lower classes. So we started with natural numbers. Adding 0 to the set of natural numbers, we get whole numbers. To the set of whole numbers, if we add the negative integers, then we get the complete set of integers. So integers are nothing but whole numbers and negative numbers. Then integers on the number line and the fractions together make rational numbers. And together, rational and irrational numbers make real numbers. So are these the only numbers that exist? In your higher classes, you will learn that the number system consists of real numbers and imaginary numbers. This part is optional. This is only as an extra knowledge. And rest of the chart depicts the same thing that we saw earlier. So the real numbers are of two types, irrational and rational. Rational numbers are made up of fractions and integers are nothing but 0, negative numbers and positive numbers. And whole numbers are positive numbers and 0. Only positive numbers are also called as natural numbers. And we also studied other types of numbers, that are even numbers, odd numbers, prime numbers and composite numbers. Can you recall the difference between prime numbers and composite numbers? Prime numbers will have only two factors, number and itself, whereas composite numbers will have more than two factors. The matter may not be very clear on this slide. This chart is taken from Google, so you can search and get the same as your copy. We also defined rational numbers, a number which can be written in the form P upon Q, where Q is not equal to 0 and P and Q are co-prime. That means they do not have common factor. In other words, P on Q is in the lowest form. And what are irrational numbers? Numbers which cannot be written in the form P upon Q. Examples of rational numbers: minus 3 on 8, 5 on 6. Even 5 is an example of rational number because it can be written as 5 on 1. Examples of irrational numbers: root 3, root 5, pi, or cube root of 2. All these square roots of numbers which are non-perfect squares are irrational numbers. Similarly, cube root of numbers which are not cubes are irrational numbers. Then we learned how to find rational numbers between any two rational numbers. So we can list any number of rational numbers between, say, 1 on 3 and 1 on 2. Remember the method? We write an equivalent fraction for these two numbers such that their denominators are same. So if the question is to find n rational numbers between these two numbers, we again express each of these rational numbers as equivalent rational numbers by multiplying n to the numerator and denominator. And then we can list down rational numbers between these two equivalent rational numbers just by changing the numerator. Likewise, we also know how to list irrational numbers between any two rational numbers. Let's say we want to write down irrational numbers between 1 upon 3 and 1 upon 2. So we convert 1 upon 3 and 1 upon 2 into their decimal form and then write down the decimal numbers between these two numbers. Those decimal numbers should be non-terminating, non-recurring in order to be irrational numbers. Then moving forward in the chapter, we learned how to convert a rational number to its decimal form. So P upon Q is a rational number. To convert it into the decimal form, we divide P, that is the numerator, by the denominator. We use simple division process. And we found that we get two types of decimal representations: terminating and non-terminating recurring. On dividing P upon Q, if the division stops, then we get a terminating decimal. If the remainder never becomes 0, then the division continues and the digits in the quotient starts to repeat, which means we get a non-terminating recurring decimal. For example, 0.8333 ... We represent the non-terminating decimal with the dots. Same thing can be written as 0.83 bar on top of the digit that is repeating. So in this example, 3 is repeating. So this is a non-terminating recurring decimal. Some numbers have many digits repeating or a block of digits repeating. For example, 0.532, and so on. So here there are 3 digits that are repeating and I can write this as 0.532 bar on top of the block of digits that is repeating. We also observed while converting the numbers into their decimal form that the number of digits in the repeating block will always be less than the divisor. So we learned how to convert a rational number into decimal number. Then we also learned how to convert a decimal to a rational number. So there are two ways of doing that. If your number is terminating type, like 0.25, to get rid of the decimal, you will shift the decimal to the right by 2 places. To do that, you will multiply and divide by 100 and then reduce it to the standard form and you get the rational number for this decimal number. But if the number is non-terminating repeating, then the idea is to get rid of the repeating part of the decimal. For example, 0.83 bar is to be converted into rational form. So we will take this number as x and then we will multiply x with 10 or powers of 10 so that we can shift the decimal to the right side, and we will obtain two equations in which the right side of the equation has same decimal part. So multiplying this equation by 10, we get 10x equal to 8.333 and so on, and x is equal to 0.8333 and so on. So on the right side of these two equations, the decimal part is same. Now we can subtract, so we get 9x equal to 7.5. So x will be equal to 75 divided by 90, and in the lowest form it will be 5/6. I have given this example so that you can recall the actual process. So we have understood about the decimal representation of rational number, how to convert rational number to its decimal form, and to convert decimal into its rational form. What about the decimal representation of an irrational number? Let's look at some examples of irrational numbers like √2, √3, √7. All these numbers can be represented in the decimal form, but you cannot use the division process here. To convert these numbers into decimal form, you will have to use the method of finding the square root of a number, which I am sure all of you have studied in 8th standard. So using that method, irrational numbers can be expressed in decimal form, and it is seen that it comes out to be non-terminating and repeating. So if we convert a real number to its decimal form, then we get two types of expansions. One is terminating, other is non-terminating. Non-terminating expansion is of two types, repeating and non-repeating. So a decimal number that is terminating is a rational number. A decimal number that is non-terminating, repeating, is also a rational number. A decimal number that is non-terminating, non-repeating is an irrational number. So based on the decimal representation, we can easily distinguish between the rational and irrational numbers. The same chart can be written in a different way. Real numbers are of two types, rational and irrational. When converted into their decimal form, a rational number will be either terminating or non-terminating recurring. When we convert irrational number into its decimal form, it will be non-terminating, non-recurring. We also learned how to identify a given rational number as terminating or non-terminating repeating decimal without actually using the division process. For example, P upon Q. Without dividing P by Q, we can say whether this number will be terminating or non-terminating recurring. What is the condition for that? If the denominator Q can be expressed as product of prime factors 2 or 5 or both, then this number will be a terminating decimal. But if there is any other number other than 2 or 5, then P upon Q becomes non-terminating decimal. For example, 1/8 will be terminating. Clearly, the denominator can be written as 2 into 2 into 2. So it satisfies this condition, and therefore it will be terminating. But if my number is 5/6, then 6 is 2 into 3. It has a factor 3 other than 2 and 5. So this number will be non-terminating, repeating. And we had shown earlier that 5/6 is 0.83 bar. Moving on in the chapter, we also learned 3 different methods of representing a real number on the number line. We represented irrational number by finding Pythagorean triplets or using simply Pythagoras theorem. We also represented irrational numbers on the number line using the geometric method, or we can call it as semicircle method. So please be thorough with all types of representation, because this part of the chapter can be asked as a 3-mark question in the paper. Also practice enough so that you acquire the skill and neatness that is required. I will not go over these methods in this video. If you have any doubts regarding these methods, rerun the videos in which they are explained in detail and try to understand from there. Next, in the chapter, we learned how to add, subtract, multiply, divide expressions containing real numbers using the rules that are listed over here. So, root a b equal to root a into root b. What does this mean? If we have root 2 into root 3, then we can multiply these two numbers and write it as root 6. But if we have root 2 plus root 3, you cannot add them. You can add them only when they are in their decimal form. We know that root a into root a is equal to a. So, root 2 into root 2 will be 2. Also, we can add two numbers if they have same irrational part. In this example, the two numbers do not have same irrational part, so we cannot add. But if the irrational parts are same, then we can add those two numbers. For example, if it is 2 root 2 plus 3 root 2, then these two numbers can be added as their irrational parts are same, and this can be written as 5 root 2. To obtain the third and the fourth rule, we use the algebraic identity x plus y into x minus y equal to x square minus y square, and we get the right hand side. In the fifth rule, we multiply each term of the first bracket with the second bracket, and so we get this product. And the sixth rule is nothing but x plus y the whole square equal to x square plus 2xy plus y square. Coming to the next part of the chapter, we studied rationalizing. For example, numbers like 3 plus root 2 divided by 4 plus root 2. This number has an irrational part in the denominator. So the idea is to get rid of this irrational part. So the process of getting rid of this irrational part is called as rationalizing. Now, in order to get rid of the irrational part in the denominator, we will have to multiply this expression with a rationalizing factor. So, in this example, the rationalizing factor will be 4 minus root 2. So that 4 plus root 2 and 4 minus root 2 will give us a square minus b square, and that helps us in getting rid of the irrational part from the denominator. So we multiply this number by 4 minus root 2 and divide by 4 minus root 2. The numerators are to be multiplied like we multiply an algebraic expression, and the denominator will be 14. So this will give us 12 minus 3 root 2 plus 4 root 2 minus 2. Now we can add 12 and minus 2, which is the rational part, and that gives us 10. We can add these two numbers because they have same irrational part. So minus 3 plus 4 will give us plus 1 root 2 whole divided by 14. So what we have done is we have written an equivalent number to the given number by multiplying a factor, and that factor is called as rationalizing factor, and it helps to get rid of the irrational part of the denominator. And based on this, we have practiced many different kinds of questions from the exercise, and I have given you some extra questions as well. Please go over them. In last part of the chapter, we studied laws of exponents. I have listed the laws that we have studied, and you have been studying this from lower classes, but the difficulty level of the problems goes up when you are in grade 9. There are two more laws that you need to remember. A number to the power 0 will always be 1, and if you have a number to a negative power, then you can get rid of the negative sign in the power by taking the reciprocal of the base. So when two numbers of same base are multiplied, then we can add the powers. If you have two numbers that have the same base and they are dividing, then we can subtract the powers. This is example for the third rule. For the second rule, we can write an example, say 5 to the power 2 whole to the power 3 is 5 to the power 6. Likewise, you can write an example for the fourth one, 2 to the power 2 into 3 to the power 2. When you have different base but you have the same powers, then you can take the power common, so this becomes 6 to the power 2. Practice enough questions to acquire the skill of using these laws in problem solving. Here is a mind map for this chapter. This mind map gives you a quick revision of all the concepts that are there in this chapter. If you cannot see the font clearly, download it from Google. This is taken from Oswald reference book. That is all in today's video lesson. See you in the next virtual class. Until then, goodbye.